Now let us solve one or two problems to finish this. We have this 250 mm diameter. Pi flush entrance friction factor is given 0.026. The pipe length is 1000 m long. It deliver water from higher riser wire to a lower riser wire here. The difference between is 75 m. This delta Z, which is given 75 m after a valve near the downstream, and is suddenly open. Now when we suddenly open this valve, what will be the steady flow velocity? In this SP, what will be the steady flow velocity? We already discussed in the previous lecture. Develop an equation for steady flow velocity. And how long after the valve is open will the flow velocity be? 1/3 and 2/3 of the steady velocity. We already discussed this topic the last topic in the previous lecture where we study approach. The topic was approach to study flow, so we equations there that you can use now. L by D is 4000, so it is greater than 1000. We can neglect the minor losses. This is the K that we discussed previously. So now in this case this is 0 and this is 0 clear because we neglect the minor losses. We have submerged discharge. This will include this submerged discharge coefficient, so that's why we only have FL by D. So this is given. We can calculate K. Everything is given. Just plug in the value. We can calculate K, and this is the formula that we developed in the last lecture for study flow velocity 2 grams H by K. What is H? H is your delta Z now in this case, so you put the values in 3.76 m per second. This is the steady state velocity. Now it is asked that what is the time that we will approach versus the steady state velocity. How much time? This we developed in the last lecture. 1/3 of this, how much time it will take that the velocity will approach the steady state velocity, and 2/3 of the steady state velocity. So for V is equal to 1/3 of the steady state. The time is, you just put values in this equation. Here 1772 seconds, and for 23 of the steady state velocity when we approaches 2/3 of the steady state velocity, the time taken is 4.11 seconds. So this we discussed in the previous lecture. Now next, we have water flows at 10 foot per second and 400, featuring long steel pipe of 8 in diameter with 2-inch thick walls. Calculate the pulse interval TR return trip and the maximum pressure rise theoretically caused by instantaneous closing the end well. Now instantaneous closing the end valve, so we calculate Cj. The joint celerity of pressure wave C is given. F and E are given, so we can easily put the values. This is now Cj, city of pressure waves. Joint or combined. When J is written means the combined, because here we treat the pipe and the fluid both is elastic. The return trip, round trip of the pressure wave, we already discussed. It is given by 2L by Cj, so you put the values now in. When you completely close the well, what is the maximum pressure rise? So when you completely close the well, this is the formula we just discussed and derived this earlier. Delta P equal to rho Cj into V. So just put the values. This is the increase in pressure, and this is in pressure head in terms of feet of water in the second case with partial closure. Cj and P remain the same, partial closure. But now we have V2 because it is not complete closure. When it is complete closure, this is 0. And this was the formula in part A, but now we are still closing. It's not, so that's why the velocity is not reduced to 0 to V2. So then in that case, it is given 6t per second, partially reducing the velocity to 6t per second. It is given, so just you put the value, and now in this case the pressure is this much. Now see what was the pressure in part A, 79,000, and now in here what is the pressure? Around 32,000 pounds per square foot. So that's why slow closing the valve, it will keep the pressure less. This is what we studied earlier. This is a problem from th edition of the textbook. The elasticity and dimensions of the pipe are such that the celerity of the pressure wave is this. Now Cj is given. Suppose the pipe has length of 600 met. This is 600 m length pipe and the diameter of 1.2 m. The flow rate is initially 0.9 cubic met per second. That is charged water is flowing. Find a water hammer pressure for instantaneous valve closure. So now we need to calculate for instantaneously time T equal to Z. What is the Pressure, so we calculate the velocity discharge. Is given velocity is 796, and now for instantaneous. Valve closure delta P is RCJ into V. This is what we discussed, so just you put the values. This is the pressure 764 kN per square meter when you suddenly close the valve in time t equal to Z. Then this will be the increase in pressure. The water hammer pressure clear part B is approximate pressure at valve. This is the valve if it is closed in 4 seconds. Now the valve is closed in 4 seconds. How much increase in pressure will occur? So now it is not instantaneous closure, because for instantaneous closure now here Tc is what this 4 second is your Tc. Now it says that when Tc is 4 seconds, so what will be the increase in pressure? So we need to first calculate that it is slow closure or rapid closure, so we need to calculate the round trip of the pressure wave. So it is how much? 1.25 seconds, and you close the valve in 4 seconds, so it means it is less than the time of closure, so it means it is slow closure. So for slow closure we develop this equation delta PD is equal to 2L by Cj, T is equal to delta P. So now we have to denote delta P. From here you can plug in the values, and now for slow closure it is 238.5 K kiln per square meter cop Pascal. So you can see 764, and then with slow closure the pressure is 238.5. That's why we would like to slowly close the V to keep the water hammer pressure reduced. Part C is what is part C? The water hammer pressure at 12 if it is manipulated so that the flow rate drops from 0.9 to 3. Now the flow rate drops from 9 to 2.3. The discharge is reduced. So what is the water hammer pressure? So now for case of the partial closure, because the flow is reduced to 3, now the V2 is 262 m 4.392.3. we reduce clear, so now instead of rho Cj into V we have V2 because it is partial closure. If it is complete closure, V2 will be 0. So now you can plug in the values and you can calculate the water hammer pressure. And for D, maximum water hammer pressure at point in the pipe 90 m from the riser wire. If a 1 second valve close closure reduces the flow rate from 3 to 0, so now you close the valve in 1 second. What is that? What is the time of return trip? 1.25, and now you close the valve in 1 second. So what is that? Rapid closure clear. So for rapid closure we first calculate x naught. Tc is now 1 second. Cj is given. We can calculate x naught, so it means that any point less than x kn will experience a pressure less than the maximum pressure, but any point greater than x naught will experience the maximum pressure. This is what we saw. This is what we say clear. So in this case what I want to say is that up to this x naught for 80 m all the points will experience the maximum pressure, but any point less than that will experience a pressure less than the maximum. Why? Because the unloading pressure wave has returned and it will not allow the pressure to reach to the maximum value. This pressure, which is here, it cannot reach to this maximum value. Why? Because the unloading pressure wave has returned and it keeps it to lesser than the maximum value. This is what we studied earlier. So now it is asked to calculate the pressure at what? 90 meters. So 90 meters is less than 480 m. That's why this pressure will not be occur at 90 m less than that. So that's why for that we calculate the velocity 4.3, and now we calculate the pressure delta P that is equal to 254, because the maximum pressure hammer at the point in the 59 meters reduces now the flow rate from 3 to 0. So that's why for 3 now the maximum pressure that can occur is this. So now we can compare. This is now on 9480 delta P. We can calculate from similar triangles. So at 90 m, delta P will be equal to similar triangles 254 id 480 equal to delta P by 90. So 90 comes here 47.7 kilopascal kiln per square meter. This will be the pressure that will develop at 90 m from here due to the water hammer, but it will not reach to 254. Why? Because it tried to reach to 254 but the UN pressure wave has reached and it will keep it to 47.7 K per square meter.